Hello, everybody, and welcome in part 4 of chapter 4, time response. In this part, in fact, we need to know how to get Laplace transform solution of a state equation. So first, we need to look into state space representation. So state space representation, it's x dot equal ex plus pu, and the output equation is y equals cx plus du. So this is state space representation. We call this one a state equation, which is a set of first order differential equation. And this one, it's the output equation. It's called the Laplace transform of state space representation, right? Laplace transform solution of a state equation. So first we will, for the state equation, we will take Laplace transform of both sides. So Laplace transform of x dot, it will be s x of s minus x0. This is the initial condition, equal a multiplied by x of s plus pu of s. We need to get x of s in one side. So we will take this one to the other side. So it will be sx of s plus a of x. So it will be s x of s plus ax of s, sorry, minus, equal x of 0 plus bu of s. We will take x of s as a common factor. When you take s of s as a common factor, you have to multiply s because s is a scalar. You need to multiply it by identity matrix I. So it will be si minus a multiplied by x of s. And also, remember, in matrix multiplication, it's very important to consider direction. We are multiplying from right, so we need to take this one from the right. So it will be si minus a multiplied by x of s equal x0 plus pu of s. We need to solve for x of s. So we will multiply both sides by the inverse of this is a matrix. So we will multiply from the left side by the inverse of this S matrix. So in this case, Si minus A inverse multiplied by Si minus A, it will be 1. So it will be just x of S equal Si minus A inverse multiplied by x of 0 plus Si minus A inverse multiplied by u of S. So we have Si minus A inverse. We can take it as a common factor. So what will remain will be x0 multiplied by p u of s. If you want to get Si minus A inverse, it should be the adjoint of this matrix divided by its determinant. So to get the inverse of this matrix. After getting x of s, we need to get y of s. So we will take Laplace transform of the output equation. Output equation was y equals cx plus du. This is the output equation. Take in Laplace transform of this one. So it will be y of s equals cx of s plus du of s. So just substitute x of s here, right? So I will write it here. X of s was si minus a inverse multiplied by x0 plus bu of s. So just to multiply it, remove x, substitute x of s with this one. So it will be c si minus a inverse. And also, in fact, we will assume initial condition equals 0. So it will be c si minus a inverse bu of s. Right? So now I need to get the transfer function. Transfer function will be y of s divided by u of s. So in fact, a plus d. In fact, I forgot plus d u of s. So it will be s, okay, xs of s. So it will be csi bu of s plus du of s, right? So take u of s as a common factor, divide both sides by u of s. So transfer function will be y of s divided by u of s will be c. I will write it here. So y of s divided by u of s will be c multiplied by si minus a inverse b plus d. This one will be my transfer function. the roots of, when you substitute Si minus A inverse, it will be the adjoint divided by determinant Si minus A. So the roots of that part, in fact, we call it will give us the roots of my system, right? Because this is a determinant of Si minus A, it will give us the characteristic polynomial or the characteristic equation of your system. Eigenvalues of the poles. Poles of a transfer function determine the nature of the transient response of the system. We know that. We understand this from the whole lecture. Is there any equivalent quantity in the state space representation which yields the same information? Yes, it will be the roots of the determinant of Si minus E. We call it eigenvalues of the system matrix. Those are, we call it the eigenvalues of your system matrix. So system poles will be your eigenvalues. So if you have transfer function, you can get from the transfer function the system poles, which will be the roots of the characteristic equation, right? And if your system is represented in a state space representation, we need to get the eigenvalues. Eigenvalues are the system poles. So if your system is in a transfer function, you can get those poles directly from the characteristic equation. If you have state space representation, you get the eigenvalues of A or of Si minus A, right? Right? It's just A, right? Those are the eigenvalues. So your eigenvalues will be your system poles. So now we have an example. You have this system represented in a state space representation, x dot equal Ax plus Bu, y equal Cx. These are the initial conditions, right? We need to solve the state equation and obtain output for the given exponential input. This is my input. So u of t equal exponential minus t. We need to solve this equation. We need to get y of t. And after that, we need to find the eigenvalues of the system poles and the system poles, right? So to solve it, we need to get Si minus A first. Because if you need to get so first we will solve this problem by finding the component parts. We just need to know, okay, y of s divided by u of s, it will be C Si minus A inverse B plus D. So first we need to get Si minus E. So multiply S by identity matrix. So it will be like this one because it's a 3 times 3, so it will be S0, 0, 0, S, 0, S0, 0, 0, S. Subtract it from A, you will get this one. We need to get the inverse. So the inverse will be the adjoint matrix divided by the determinant. This one will be determinant. U of t equal exponential minus t. So its Laplace transform U of s will be 1 divided 1 minus 1. So it will be s plus 1. So it will be 1 divided by s plus 1. So now we can get x of s. So x of s will be Si minus A inverse multiplied by x0 plus Bus, right? So just to substitute. So we will get, we will solve it we will get the 3 states. We have x1, x2, and x3, for example. But in fact, it was better to just do matrix multiplication, but it will be very complex here, right? So once you have those states, you can get y of s. So y of s will be c multiplied by x of s. So it will be x1 of s plus x2 of s. So we can get summing this one with this one, we will get y of s. So y of s will be this, right? And so we need to look, we will use partial fraction expansion, right? So it will be k, this one, it will be k1 divided by s plus 1 plus k2 divided by s plus 2, and so on. K3 divided by s plus 3 plus k4 divided by s plus 4. For s plus 1, we found that k1 is very small, right? So we canceled it. We did this pool zero cancellation. So we ignored that part because K1 was very small. So finally, we will approximate this one, and it will be this one. We will apply inverse Laplace transform, so we will get y of t equal minus 6.5 exponential minus 2, plus 19 exponential minus 3, minus 11.5 exponential minus 4. If you want to get this eigenvalues, for example, so we need to look into the determinant of this equation. So we will go back to that part, this part, and factorize it, because it will give us the system pools, right? In fact, we did that here, so it's s plus 1 multiplied by s plus 2 multiplied by s plus 3 multiplied by s plus 4. So in this case, we have pools at minus 2, minus 3, minus 4. Okay, so now we will do it with another system. You have this skill assessment exercise, x dot equal x plus pu. The same input also, it's exponential minus t, y equal x0. Solve for y of t using steady space and the Laplace transform techniques. This one should be much easier. So first we need to get si minus a. So it will be this one, it will be s0, 0 s minus a, what a? It's 0 minus 3, 0 minus 3, 2 minus 5, 2 minus 5. So it will be s minus 0, it will be s. 0 minus 2, it will be minus 2. 0 minus minus 3, it will be plus 3. S minus minus 5, it will be s plus 5. We will get the inverse. So the inverse will be the adjoint. So it will be, just replace this one with this one, and multiply this one by 0. So it will be s plus 5, s, this one 2, this one minus 3 divided by determinant. It will be s multiplied by s plus 5 minus minus, so it will be plus 6. So it will be s times s plus 5, it will be s squared plus 5s plus 6. So we will get bu, it will be this number. So we will just substitute into this equation. X of s will be si minus e inverse multiplied by x f0 plus bus. Bus, it will be that part, and the initial conditions 2 and 1, right? So in fact, it will be 2. This one, it will be like 2, 1, multiplied by b times u. What is b times u? B times u, it will be 0, 1, multiplied by this exponential minus t, so it will be 1 divided by s plus 1, correct? So this one will be 0, 1, s plus 1, so it will be that part. Add to it x0, initial conditions, so it will be 2, 1, so it will be, this one will be 2, here it will be s plus 1, here it will be s plus 2. Will be like this. Multiply this one by this equation, by the inverse. Multiply this one by this equation. So you will get x of s. So it will be 1 divided by that part, which is it was better, in fact, to not multiply this one here because we can get it out. So it will be s plus 1. This one 2 times 3, so it will be s plus 2 times s plus 3. Multiplied bu, it will be just, and make it easy by, instead of multiplying it. Yeah, we have to multiply it, in fact. We have to multiply it. We take it as a common factor, yes. We got it as a common factor from inside. So it will be s plus 2, and here 2 multiplied by s plus 1, right? So do this multiplication, you will get this one, that part. So now we have x of s. We need to get the output. Y of s, it will be just cx. C multiplied by x. So do this multiplication, you will get y of s equal that part. Do partial fraction expansion. So it will be minus 0.5 divided by s plus 1, minus 12 divided by this, plus 17.5 divided by z. Take inverse Laplace transform. So it will be minus 0.5 exponential minus t, minus 12 exponential minus 2t, plus 17.5 exponential minus 3t. Now we need to find the eigenvalues. Eigenvalues, if you want to find the eigenvalues, it will be the roots of the characteristic equation, which is that part, right? So this characteristic equation, it's s squared plus 5s plus 6. Factorize it, so it will be s plus 2 multiplied by s plus 3. So we will have two eigenvalues at s minus 2 and s minus 3. So now we can get, we have two system poles at minus 2 and minus 3, right? Time domain solution of state equation. I mean, its approach, it's called the state transition matrix, which is used instead of using Laplace transform. It's a little bit complex, but it's also not a big deal, in fact. So we try to find the time domain solution of the state equation instead of using Laplace transform, which is much easier. We can use this something called the transition matrix, a state transition matrix, using something called the state transition matrix. So the solution here, it will be x of t. It will be exponential at multiplied by x of 0 plus integration from 0 to t, exponential a t minus y, t minus tau, multiplied by bu of tau d tau. So we will use something, we will define exponential at as phi of t. We call it state transition matrix. So this one will be phi of t. This one also, it will be phi, but instead of t, it will be t minus tau. And what is phi of t? Phi of t, in fact, it's a Laplace transform of Si minus A inverse. Phi of t, the state transition matrix, it will be the Laplace transform of the of Si minus A inverse. So first, we need to get phi of t. Once you have phi of t, you need to substitute it into this equation. Once you get x of t, you can get y of t. So how to get the state transition matrix? We have this state space representation, x dash t or x dot of t equal ax plus pu, yt equal cx plus du. So the behavior of xt, we need to solve it. So there are those homogeneous solution for x of t and the non-homogeneous solution of x of t. Homogeneous solution, x dot equal ax of t. So we will apply Laplace transform. So it will be sx of s minus x0 equal a multiplied by x of s. We will ignore the input to get this homogeneous solution. So in this case, x of s will be si minus a inverse multiplied by x of 0. So we just ignore inputs, all inputs. So now we will apply inverse Laplace transform. So x of t will be Laplace transform of si minus a inverse multiplied by x0. This part, in fact, we call it exponential. I mean, if you need to solve this one, what does this mean, in fact? This one means it's 1 divided by Si minus A. We need to get inverse Laplace transform of that part. But remember, it's matrix notation. So inverse Laplace transform of that part, it will be exponential. Minus A, it will be A multiplied by T. So x of t here, it will be exponential a of t, which is the Laplace transform of that part multiplied by x of 0, initial condition. So this is the definition of a state transition matrix. So phi of t equal exponential a of t, which is the Laplace transform of Si minus A inverse. You can just, I mean, you can substitute, I mean, those initial conditions. So x of t0, for example, it will be e exponential a multiplied by t0 multiplied by x of 0. So now, if you want to get x of 0, you need to multiply from the right-hand side by exponential minus at. So multiplying by from right-hand side, from left-hand side by exponential minus at. Multiply here also by exponential minus at. So in this case, x of 0 will be exponential minus at0 multiplied by x of 0. We need to get x of t. If you want to get x of t, so it will be x of t equal exponential AT multiplied by x0, this equation here, right? So it will be exponential AT multiplied by x of 0, and x of 0 equal that part. So it will be exponential A, take A as a common factor, it will be t minus t0 multiplied by x of 0. So x of t will be phi of t minus t0 multiplied by x of 0. So they call it the state transition matrix because you can, those are the properties of it. So phi of t, it will be exponential E of t, which is Laplace transform of Si minus A inverse. And phi of 0 equal this equals the identity matrix. So phi of 0 equal, if you can put t equals 0 here, so substitute t equals 0. So it will be exponential A multiplied by 0, it's exponential 0, it equal identity matrix. This identity matrix, it will be just maybe this 1, 0, 0, 0, 1, 0, 0, 0, 1, right? For 3 times 3. Inverse of phi, the inverse of phi of t, it will be phi of minus t, right? Yeah, because if you want to take the inverse of phi of t, it will be phi of minus t. X of 0 equal phi of minus t multiplied by x of t, phi of t2 minus t1 multiplied by phi of t1 minus t0, it will be phi from t2 minus t0. Phi of t to the power of k, it will be phi of k times t. We don't want to go into much details here. If you want to get, this is a homogeneous solution. If you want to get non-homogeneous solution, we will start from the state space representation and we will solve it using, without ignoring the input, right? So take inverse Laplace transform of this one. So it will be Sx of S minus x0 equal Ax of S plus Pu of S. So this one will go to the other side. This one will go to this right-hand side. So it will be Si minus A multiplied by X of S equal X0 plus Pu of S. Multiply both sides from the left-hand side by inverse. So X of S will be Si minus A inverse multiplied by X of 0 plus Si minus A inverse multiplied by Pu of S. You want to get X of t, apply inverse Laplace transform to this equation. So it will be inverse Laplace transform of that part multiplied by X of 0 plus inverse Laplace transform of that part, the whole part. So we will call that part phi of t multiplied by x of 0 plus, if you want to get that part, so it will be integration from 0 to t, phi of t minus tau multiplied, it's called the convolution because we have those two integration of, it's Laplace transform of multiplication of two functions, right? So we'll use this convolution. So it will give us integration from 0 to t, pi of t minus tau multiplied by p u of tau theta. We have here an example. We have state space representation x dot equal x plus pu. We have the initial conditions equal 0. So we will start by finding the state transition matrix. It will be inverse Laplace transform of Si minus A inverse, which is exponential AT. Exponential AT, it will be, this is A matrix. This one, it's A matrix. So it will be, we need to get first Si minus A inverse. In fact, we need to get this one, Si minus A. So I can do it here. So Si minus A, it will be S0, 0, S minus A matrix, which is 0, 1, minus 2, minus 3. So it will be S minus 1. It will be 2, S plus 3. We need to take the inverse, Si minus A inverse. I will do it here. So it will be s plus 3 s1 2 minus 2 divided by determinant, it would be s squared plus 3s plus 2. So it will be s plus 3, 1 minus 2, 5 divided by factorize, it will be s plus 1 multiplied by s plus 2. Divide this one by this one and use partial fraction expansion, right? So I can say that it will be equal k1 divided by s plus 1 plus k2 divided by s plus 2. The first term s plus 3. This one also will be like k1, k2, k3, k4. So we need to repeat this one, partial fraction expansion. We need to find the k1, k2, k3. So this part k1 here, for example, it will be 2. So when you apply inverse Laplace transform, it will be 2 exponential minus t minus exponential minus 2t. Here k1, k3, k4, right? 1, 2, 3, 4. Here 5 s plus 1 plus k6 divided by s plus 2, k7 divided by s plus 1 plus k8 divided by s plus 2. So we will do this one and we will get this coefficients, right? We will get 5t. Once you have this 5t, you will apply this equation and you do this integration and you will get your x of t. So the solution will be this one, x1 and x2. Once you have it, yes. Okay, so I prefer to use this one. This one takes time, but it's okay, right? We can do it. Okay, so this is the solution in details for this example. X dot equal x plus pu, y equal x0 equal 1 and 0. So first we need to find the eigenvalues by finding the determinant of si minus a, which will be s squared plus 6s plus 8 equals 0. So this one will be s plus 2 multiplied by s plus 4 equal 0. So we'll have an eigenvalue at minus 2 and another eigenvalue at minus 4. So you can write, we have those eigenvalues. So we will have those exponential terms. So you can write phi of t directly equal. It will consist of those 4 terms. So it will be k1 exponential minus 2t plus k2 exponential minus 4t. 3, 4, 5, 6, 7, 8. And you can just know that from the properties of state transition matrix, phi of 0 equal I. So if you put t equal 0, this one will equal I, which is 1, 0, 0, 1. When you do it, you will get k1 plus k2 equal 1, k7 plus k8 equal 1, k3 plus k4 equal 0, k5 plus k6 equal 0. So this is the first set of equations. You can differentiate this for phi dash of 0 equal a, right? Because phi of t equal e exponential t. Differentiate, so it will be phi dash of t equal a exponential at. Set t equal 0, so phi dash of 0, it will be a exponential a multiplied by 0, which is equal a. So phi of 0 equal, phi dash of 0 equal a. Substitute, get set of equations. Solve those equations together. You will get values for k1, k2, k3, k4, k5, k6, k7, k8. So this is one way for solving it. After that, you need to find phi t minus tau multiplied by b. Phi of t multiplied by x of 0. Substitute into find this integration. And finally, just combine your solution to get x of t. So x of t will be phi of t multiplied by x of 0 plus this integration. So you will get x of t. Now you have x1 of t and x2 of t. Using Laplace transform, we did that already, but we can do it one more time. So first we need to start by getting si minus a inverse. So we will get si minus a. You will get si minus a inverse, right? We will do it. Factorize that part. So that part will be s plus 2 multiplied by s plus 4. It will be like this one. Use partial fraction expansion. solve for K1, K2, K3, K4, K5, K6, K7, K8, and apply inverse Laplace transform. When you apply inverse Laplace transform, 5t, it would be 2 exponential minus 2t, minus 1 exponential minus 4t, 1 divided by 2 exponential minus 2t, minus 1 divided by 2 exponential minus 4t, and so on. So we will get 5t. You have this example here. Solve for state transition matrix. We need to get 5t. So, right? So 5t, how we will get it? So 5t will be inverse Laplace transform of Si minus A inverse. We need to get that. So first we need to get Si minus A, right? Which will be S minus 0 minus 2 to S plus 5. We will get Si minus A inverse. So it will be something divided by S squared plus 5S minus, so it will be plus 4. Here it will be S plus 5, S 2 minus 2, right? So it will be S plus 5 divided by S plus 4 multiplied by S plus 1. 2 divided by S plus 4 multiplied by S plus 1. Minus 2 divided by S plus 4 multiplied by S plus 1. Here it will be S plus 5 divided by S plus 4 multiplied by S plus 1. Use partial fraction expansion and apply inverse Laplace transform to get those coefficients, right? And get 5t. Once you have 5t, you will apply the equation to get x of t. So x of t will be 5t multiplied by x of 0 initial condition plus integration from 0 of t, phi of t minus tau multiplied by p u of tau d tau. And you will get x of t. Once you have x of t, you need to get y of t. Once you have x of t, multiply it by this vector, you will get y of t. So it will be 2 times x1 plus x2. You will get this one. So use, okay, so I have here the solution. So we will get first 5t. Once we have 5t, we need to get 5t minus tau. And after that, b multiplied by u of tau, right? Substitute into the equation, do the integration, you get x. You get x of t equals that part. Multiply that part by c, which is 2 and 1, you will get, okay, so I have a problem here. Yes, so we will get the solution. So for this, I mean, it's not a report because we have a second home assignment. I will prepare it soon and I will post it in Canvas. But if you want to solve a problems for practice, we have many problems in this chapter. You have problem 2, 4, 6, 8. All those problems are very similar to the problems which we solved in the examples and in skilled assessment exercise. So please to try to solve it. And next time, we will go to chapter 6 where we will check system stability. So next time, we will talk about stability in chapter 6. So thank you very much for watching my videos. And if you have questions, please contact me immediately. So thank you very much.